the BBC presents the first in a series of 7 talks by British astronomers under the general title The ABC of the Universe. Dr Raymond Lyttelton, reader in theoretical astronomy at the University of Cambridge, gives today's talk, which he calls Our Own Solar System.
Luckily for me, most of you, I think, probably have a fair idea of what the solar system is like. It's the isolated assemblage of planets, minor planets and comets that move round the Sun. The 9 major planets pursue almost circular paths, almost all in the same plane, and move in the same direction, so that looked at, as it were, from on top, the solar system is a flat, round disk, with the planets all making concentric circles round the Sun. To give you an idea of the scale of the system, the Earth itself is a comparatively small planet, though large enough to hold a considerable atmosphere, fortunately for us, and it lies about 150 million kilometers away from the Sun. The planets furthest out, Neptune and the tiny Pluto, are at about 30 times this distance. Jupiter, the largest of the planets, has 300 times the Earth's mass, but even so, it is only 1,000th of that of the Sun, which sits at the center, controlling the scene just because of its great mass, which holds the planets in their orbits with the pull of gravity. Besides moving round the Sun, most of the planets spin rapidly like tops. Jupiter and Saturn turn round completely every 10 hours. But attaining even our present limited understanding of the system has been a long and complex process. Indeed, the first great step towards the whole of modern physical science was the recognition, some 4 centuries ago, that the Earth itself is not the fixed, immovable thing it seems to be, but instead is a rapidly spinning sphere hurtling round the Sun. It was this new concept that opened the way to finding out the arrangement of the other planets and how they move, and that enabled Kepler to discover the rules of planetary motion. And this great achievement led on to the invention by Isaac Newton in the 17th century of precise mathematical laws of motion, which not only enable the minutest details of the movement of planets and other bodies to be predicted for centuries ahead, but also have been applied to make plain the fundamentals of all mechanical matters. How old is the solar system, and how did it come into being? It has not been in existence for all eternity. The Sun itself cannot be infinitely old, since it shines by steadily converting its hydrogen into helium, producing energy like a controlled hydrogen bomb, and yet it has used up only a few % of its total fuel store. And the planets show their comparative youth by the nature of their atmospheres, and the distances of the moons that revolve round them. Then in the rocks of the Earth itself, we find that radioactive transformation of uranium into other elements indicates an age for our planet of not more than 5,000 million years as an independent body. We are then forced to consider, how did this system of planets come to be? But before looking at the various theories that have been put forward, I must admit at once that none of them are really satisfactory, and the problem remains largely unsolved. The early theories all adopted unquestioningly the idea that the planets originated at the same time as the Sun. Later, astronomers turned their attention to so-called catastrophic processes, suggesting that some violent event in the history of the Sun had drawn out of it the material from which the planets were formed. Another star passing exceptionally close by, it was thought, could draw out part of the Sun, just as the Moon draws up the Earth's tides. Or if the star had come closer still, it could actually have forced out the planetary material by a gigantic side-swiping collision, a string of droplets separating out as embryo planets from the connecting streamer as the 2 stars separated again. But detailed investigation of these ideas finally proved that such mechanisms could not produce a planet as far out from the Sun even as the nearest planet, Mercury. Never mind the massive Jupiter, which is more than 12 times as far out. This made astronomers suspect that possibly the Sun might not be the original source of the planets at all. They attempted to save the catastrophic theories by considering the possibility that perhaps at some stage the Sun had been a double star, and that its companion, held to it by mutual attraction, had supplied the material for the planets, when it either collided with something else or exploded. Such a companion would have been likely to have been far enough away from the Sun to account for the great range in space of the planets. This sort of theory was satisfactory in terms of dynamics, the mechanics of moving bodies, but advances in physics and chemistry soon began to throw further doubt upon it. It seemed unlikely that planetary material pulled out of a star at such high temperatures could condense quickly enough into compact planets. And astronomers also found an awkward difference in the makeup of Sun and planets. The Sun is more than 90% hydrogen and helium, but it is the heavier elements, rather than these light gases, that are abundant in most of the planets. So theory began to take a new turn. Instead of primitive planets forming at once, astronomers now believed that the released gases, in order to cool, would expand rapidly and spread out into a flattened ring, completely encircling the Sun and revolving round it. When this ring finally cooled, it would be made up of tiny solid particles, together with such gases as could still exist at the prevailing temperature. Simple accumulation through collisions would snowball these solid particles together. And the larger a particle grew, the greater would be its chance of collecting others. Tens or hundreds of millions of years may have passed. There's no hurry about astronomical processes. Before some accumulations, having by chance gained an early lead on others in their neighborhood, would have become so large that their gravitational force could now reach out, as it were, and gather in particles from further and further away. These successful accumulations would finally produce the major planets, and this theory explains their orbits as well. Circular orbits in the same plane would be automatically produced, because this is how the original disk must have moved owing to collisions between its particles. The original disk of gas may not have come from the Sun or a companion at all. The vast spaces between the stars contain large numbers of thin clouds of gas and dust, and the Sun passes through such clouds every few million years at least. If it had chanced to meet one at sufficiently low relative speed, it could have gathered to itself a huge quantity of material from the cloud, enough to form all the planets. And since these clouds themselves rotate slowly, the gas thus captured would form into a disk rotating round the Sun at a speed that would increase as the captured material was pulled in. This would account for the huge orbits of the planets round the Sun. Yet another possibility is that the disk of gas from which the planets formed was made at the same time as the Sun itself, as it condensed out of the interstellar gas. It may be that just such a disk is needed, so to speak, when a star is formed, to slow down its rotation, acting as a brake as the star condenses to smaller and smaller size. It may be that magnetic forces transfer the rotation from the central star to the disk material, much as the spokes of a wheel operate to rotate the rim when the central axle is turned. Such forces would drive the gas out to something like the distances of the planets, while at the same time slowing down the central star to the very slow rate at which the Sun spins today. It takes nearly a month to turn round once. Now obviously, if this latter type of theory turns out to be valid, it would imply that a fair proportion of stars will have formed attendant planets, perhaps something like 1%. Even this would mean hundreds of millions of planetary systems in our own galaxy, and there are thousands of millions of other galaxies. Here and there, among all these possible solar systems, there might well be planets just as suitable for life as is our Earth. I should stress that proving or disproving such theories is the only means whereby we can make any progress with the question of whether life, or suitable conditions for it, exists elsewhere in the universe. For it is beyond the power of any conceivable telescope to detect whether other stars may have planets moving round them. But if from general theory we conclude that such planetary systems are almost certain to exist, then we can infer something more about them by exploring more fully the planets of our own system, which are now so nearly within our reach. And yet we still know remarkably little about the conditions on the surfaces of our neighbours in space. We can only see solid surfaces on Mercury and on Mars, and even for these the distances are so great that we can come to few confident conclusions. The proximity of Mercury to the Sun makes it far too hot to support life, even were it not, as far as can be settled, devoid of atmosphere. Only on Mars does there seem the remotest possibility for life, and even there the odds are that suitable conditions are long since past. Oxygen, so necessary to animal life, can be present in the atmosphere only to the minutest extent, while the characteristic red colour of the surface suggests material consisting of metallic oxides in which oxygen may now be irretrievably locked away. This oxygen may once have been atmospheric oxygen, and if life ever once came to exist, it could well have gradually adjusted itself as conditions changed in just such a way as to survive. All this, of course, is pure speculation, and it will remain so until scientific measures can be made right there on these planets themselves. Our nearest planetary neighbour, Venus, is permanently shrouded in cloud that simply reflects the sunlight back into space and betrays little or nothing about the planet itself. Even the rotation period, the length of the day on Venus, is a matter of great uncertainty. For Mars, although the surface can be clearly seen, the meaning of the changing dark markings and the exact nature of the brilliant frost that covers the polar regions in the Martian winters are still matters of conjecture. Above all, there is the great outstanding question whether any form of life whatever, animal or vegetable, exists on Mars. Even if only the most primitive things exist, perhaps some crude moss, such as one sees clinging precariously to old garden walls, it would be an epoch-making discovery to establish that life existed elsewhere in the universe. For it would strongly suggest what many scientists already are inclined to believe, that if conditions are favourable for life in any part of the universe, then life will come to exist through purely natural processes. This again is the purest speculation, but it may not be many years before we shall have definite knowledge of conditions on Mars and Venus, and perhaps not so many more before man himself finally sets foot on another planet for the first time. Then many of these speculations about the planets may be settled beyond argument. But it is the entirely unexpected things that we will learn about the planets that may well prove to be of the greatest interest and importance, though what these may be we cannot, of course, in their nature at present even begin to guess.
That was Our Own Solar System, the first in a series of 7 talks by British astronomers under the general title The A.B.C. of the Universe. It was given by Dr. Raymond Lyttelton of Cambridge University and presented by the B.B.C.